Hello again. As I promised you, I'm back here with the same example of the crank-slider mechanism for which I solved the problem using the using the actually absolute motion approach by, finding the position of the slider D as a function of angle theta and then take the derivative. So if you guys recall, what we were trying to do was I gave you these values of the length of the crank and the connecting rod. So what was given, given that B was 1 meter, B is 1, L was 2 meters, right? And angular velocity of the crank was given to be 10 radians per second. As you could see, it's rotating clockwise. And we wanted to find velocity of the slider D when theta is 30 degrees. Okay? So as you know, we've already done this problem. You've seen it in another video, or if you haven't seen it, I'll put the link in the YouTube, the YouTube video, so you can refer to that. In any case, the answer was the velocity of D based on that approach was 7.236 meters per second and to the left, to the right. Sorry. So, what I want to do now is to redo the same problem, trying to find velocity of D at that angle using the instantaneous center approach. So, if you guys remember from other videos where I showed how you can locate the instantaneous center, first of all, we're trying to locate the instantaneous center of what? The body that is going through combination of translation and rotation. That would be the connecting rod BD. So the question should be, where is IC of link BD at this instant when theta equals 30 degrees? Okay, so what do we need to do that? We need in general velocity of 2 points on this link. You see, velocity of B is easily determined. That would be 90 degrees to the crank and in the direction of its omega. And it can be calculated easily by saying, okay, velocity of B is R omega. R is B, which is 1 meter, and omega is 10. So that would be 10 meters per second. Look at it pointing like that. And this angle, by the way, has to be 60 degrees. Because remember, this angle right now is 30 degrees, right? Therefore, this must be 60 degrees. All right. And then what else do we have? We were trying to find velocity of D, but what we know about velocity of D is that D has no choice but to move within this cylinder. It's confined to move horizontally and obviously is forced to move to the right. Therefore, once you have velocity of 2 points on the body, how do you find the instantaneous center? All you have to do is to draw a perpendicular line to these two velocities at those points. So perpendicular to velocity of B would be just the extension of AB, like this. So that's 90 degrees to velocity of B. And perpendicular to velocity of D would be a vertical line like this, right? Let me just erase this for you and redraw it again. One more time. Try to do a better job, hopefully. Okay, so this is 90 degrees to velocity of D. The point of intersection is what we call instantaneous center. And by definition, velocity of that point is 0. It's the center of rotation. So what we are saying, in order to visualize the motion, we are saying that this link BD, connecting rod BD, is in pure rotation about C. And as I said, the way to visualize is as if we have a triangular plate like this, triangular plate CBD, rotating at this instant about C with, as you could see, and it's rotating counterclockwise with an omega of BD. And how do we use this information now to find velocity of D? First, we try to find omega BD. Once we have omega BD, then we can find velocity of D. So remember, the concept of instantaneous center is that once you locate that point, the body is in pure rotation about that point, that imaginary point, and then the problem becomes very easy, because then you could say velocity of B, for example, here. Velocity of B is R omega. But what is R? R is the distance from C, the center of rotation, to point B, times omega of the body, which is omega BD. So I already know velocity of B is 10 meters per second. I need to go and find CB. So let me show you how you find CB. So look, if I drop a line here, remember B is 1, right? So, and this is 30 degrees, so this would be 1 sine 30, which is half, 0.5. And remember, this, the length of connecting rod is 2 meters, right? So then we can go ahead and find this dimension in this triangle. If the hypotenuse is 2 and the rise is 0.5, this becomes 1.9365 meters, if you do the calculation, which is the same distance as this guy over here in this triangle. So if this is 1.9365, then I can go ahead and find, and you know that this angle is 30 degrees, right? Therefore, this becomes 1.9365 over cosine 30, the hypotenuse, which happens to be 2.236. So I find CB, right? And then furthermore, I need later on also the distance from D to C, DC, to find velocity of D. And you could see that once you have this hypotenuse here, 2.236 times sine 30, this becomes 1.118, half of actually the hypotenuse, because sine 30 is 0.5, right? So now I'm ready to finish up this problem. Look, guys, 10 meters per second equals CB. CB is 2.236 times omega BD. So go ahead and solve for omega BD. At this instant, omega BD comes out to be about 4.472. And clearly it's going counterclockwise. So now, good news is once you have omega BD, you can find velocity of any point on this body. And I'm looking for, obviously, velocity of D, right? Velocity of D. And velocity of D, since this guy is in pure rotation about C, would be R omega, and R is from C to D. So we get velocity of D is equal to R times omega, but R is CD, and omega, of course, is omega of the connecting rod, or omega of the triangle, the same thing. So velocity of D becomes, and what is CD? 1.118 plus 0.5 is 1.618 times the 4.472, and we get exactly what we're supposed to get, the 7.236, which is exactly the same number we got when we did this problem by absolute motion. I hope this is clear enough for you. I will put the link at the bottom of this YouTube video, and you can go and look at the absolute motion approach, or I'll put the link of this video at the end of the absolute motion video. Thanks for watching and listening.